So again, these slides are coming from the algorithms book. We're going to talk about Mergesort, the process. Okay, then we're going to have a look at the code. All right. So this is just an introductory slide telling you the importance of Mergesort and Quicksort algorithms. These algorithms are relatively new compared to the previous algorithms. So in both cases, they were invented in the 1970s and 80s. Okay, so it's not too far away. Now these algorithms, Mergesort and Quicksort, okay, these are considered to be one of the top 10 algorithms for the last century in science and engineering. Both of these algorithms are widely adapted, okay, by different programming languages. They're implemented in operating systems, and you'll see lots and lots of application of these two algorithms almost anywhere. So you can see some icons. Can you tell me what these icons are? Starting from go from left to right. Anyone?
I can't see the screen. I'll get out and then come back.
You cannot see the screen?
The one on the left, Java.
Okay, left is Java.
Yes. The one, the far right is Android.
Okay, Android. Good.
The camel, I have no idea. The next is C++.
Okay.
I guess the one next to it is Python.
Yes, Python.
Firefox.
Firefox browser.
JavaScript.
JS, I have no idea.
JavaScript.
JavaScript.
And Ruby. Okay.
Yes.
These are programming languages. Camel is Perl. Okay.
Camel is Perl?
So you guys are CCIA students, you should know all of these things. All right. For Quicksort, you see, what do you see?
Java, and then like Perl, as you said, and then like C, Unix, Chrome,
So
JavaScript.
Unix is operating system, Chrome browser, JavaScript. JavaScript is
It's a language. It's a scripting language.
engineering students. Anybody here from engineering?
Yes, Doctor. The one I know what this is MATLAB. The one in the
Good, MATLAB. Yes, MATLAB. And the last one?
The last two, I don't know actually. It's like
The second last is MATLAB. The last one is Visual Studio. Visual Studio or .NET Framework, .NET environment. It's commonly used in Windows operating system.
yeah. Visual Studio is the environment to develop C#.
C#, Visual Basic, .NET. Yes. Okay. Right. Let's try to understand how Mergesort works. Okay. The basic plan is 2 steps. First step is divide your space into equal halves. Okay. Divide your array or your space into 2 equal halves. That's step number 1. Step number 2 is sort each half. Sort each half. Step number 3, okay, which is recursively merge the 2 halves. Recursively merge the 2 halves. Okay, what you see in front of you is just a picture. So it's showing you the input. It's an array that contains these characters. So it shows you merge sort example. That's the data that we like to sort. Okay. What we do is we divide this in equal half. Divide the array in equal half. So first, the left side, okay? And while you're dividing it, you start sorting it. You start sorting, sort the left side, sort the right side, and then merge. Okay? So 3-step process. Divide the array. Step number 2, sort each half. Step number 3, merge the 2 halves, and you get your sorted data. That's it.
I can imagine this for like really large data, because you can't, like the computer can't process a lot of data, so you have it into 2 halves.
Okay. Yeah. So the basic plan is the same. Now the thing is, it would be your job to find out what should be the size, what should be the minimum size. How long should we keep dividing this? Okay, I'm going to show you a simple example here. We're going to show you a very simple example how this is going to work. So let's try to follow this. If you fully understand it, then we're going to have a look at the code.
It's going to half it until it reaches half the size of the original array, right?
Okay, let's try to understand how this is going to work. Okay, it's very important that you pay attention over here. If you don't follow, let me know. I will be happy to repeat it, because later on everything depends on this animation. So this is how it's going to work. First, we're going to divide the array in two parts. Okay, so right now, just for the sake of understanding, we're assuming the left side is already sorted, right side is already sorted. Right. Do you remember binary search? We used to have a formula where we used to find the middle. So middle is equal to low plus high divided by 2. Okay, so we take the low position, our index, plus high index, and divided by 2, that gives us the low, or that gives us the mid, sorry. So that's what we're going to do here. We're going to find the mid, and we're going to find the one after mid, which is mid plus 1. So use the same formula, to find the middle, and then we're going to sort the left side, and we're going to sort the right side. So here's how merge sort works. Merge sort requires you to have extra space. How much extra space? Exactly double the size of the original array. In other words, we have to create another array of the same size as the original data. So here in this particular example, I'm showing you my original array's name was A. Okay, now the copy is going to be called aux or auxiliary. Okay, it's just a copy. Now what we're going to do is we're going to start matching the left side with the right side. Whichever matches, we're going to copy that to the auxiliary array. So this is what we're going to do. We copy everything to the auxiliary array. Okay, copied everything over there. So remember, this is going to be costly. What is the cost of copying everything to the other array? In big O terms. Big O of what?
Big O of n.
Good, big O of n. So copying everything from the original array to the other array is big O of n. But it does not feel very complicated or very costly, because we already know that the sorting algorithm's runtime is n squared. So what's n squared plus n? Remember the big O notation? We only look at the highest order term. We ignore the lower order terms. So if my equation looks like this, n squared plus n, so I can ignore n because n is much smaller compared to n squared. Anyways, so now what we do is we're going to use indexes. We're going to define 3 indexes. So we have I, j, and k. Okay, so we're going to use I index on the left side of the copied array, j index on the right side of the copied array, and k index in my original array. In the beginning, I would be position 0, k would be position 0, and j would be position middle plus 1. Middle plus 1. But now what we do is we're going to compare the values at indexes I and j. Whichever is smaller, we'll copy it at k, index k in the original array. So now what we're going to do is we're going to compare A with E. A with E. A is smaller, so we're going to copy A to the original array. Okay? A goes to the original array. Once you copy A to the original array, okay, now we've already processed A, so we're going to increment. We're going to do +1 for K and J. Get it? Next.
Yes.
So that was the first step. Next, we compare C at position J with E at position I. So again, C is smaller than E, so we copy C in the original array, and we're going to increment J and K. Next, we compare E at position I with E at position J. Right? Both of them are exactly the same. But now we always have the rule, we start reading from left to right. So if they're the same, we're going to take the left one. So we take E from the left side. So we're going to copy E at position K, and now we're going to increment I and K. All right, again, compare E at position I with E at position J. So we go with the left one, E goes up. Now we're going to increment K, and which one, I or J?
J.
You sure?
No, I, because they are the same.
You took it from the left side. You took it from the left side, so I will increment. Okay. Next, E and G. We're going to compare these two. So if E is smaller, so we take E. It goes to position K. Now, which one increments, I or J?
J.
J, because you took it from the right side.
Yes.
Okay. Next, G and R. G is smaller. So we take G from left side. Now we have to increment I or J?
I.
I, increment I. Okay. Next, M compares with R. So if M is smaller, so M goes up. We're going to increment I. Okay. Now again, R and R, they're the same. So again, the same rule. We go from left to right.
The left.
So we take the left one. Okay, R goes up and I increments. Notice I has crossed the middle. Once I has crossed the middle, this means the left side is done. You already finished sorting the left side. Now what we can do is we can take R, okay, simply copy it to position K, J plus plus, increment J, take T, copy it into position K, and plus plus. So K and J have exceeded the size of the array. Fine, I have it done. Okay? So that's how merging works. So remember again, there's merge sort is a 3-step process. Okay, what's the first step?
Copy.
Divide by half.
What's the first step?
Split in half.
Split in half. Step number 2 is sort each half and then merge them. Okay. Now let me show you.
Sure.
Sorry?
There's something not clear. Can you go to the previous slide?
Before this is nothing. I mean, this is the first
Oh,
slide.
that's the next one.
Okay, this is the next one, the one I showed you.
Yes. We didn't sort RT. We just, since the left side is done, we just pushed it.
Very good point. The thing is, when you start merging, okay, your array would already be sorted. That's interesting. It's going to happen magically. We'll see this thing in a few minutes. Okay? So merge does not actually sort. Merge goes after sorting. Merge is just putting things together. So, so the array that you're going to receive would already be sorted before you merge it. Okay, let's have a look at the code. This is a part of the code. Implementation using the loop. So here's a merge method. Merge is taking 5 parameters. So we have original array A, we have the copied array aux, we have low, middle, and high. Okay? So first step is we're going to copy everything from the original array to the other array. So here's the first loop, which is running n times. Copy everything from the original array to the auxiliary copy array. Next, we're going to define the middle. Where is the middle? So we define integer I equals low, j equals middle plus 1. And then we're running a loop on k. K goes from low to high. This is what we saw in the animation. Like, if I is bigger than middle, yani we crossed the middle. And we're reading from left to right, going from 0 to the middle. If we cross the middle, okay, now what we're going to do is we can copy auxiliary j++ to the original array. Okay. Else, if j is bigger than high, then we cross the right side. The right side was all finished, we exhausted it. So we're going to copy everything from I to position k, the original array. Right. The third one is else if now we're comparing the values at position j with I. Okay? If position j is less, this means we go with the right side. So we're going to increment j++. If not, this means the left side was smaller, so we're going to increment I++. So this is a very cleverly written code. Okay, you need to look at it a few times before you will understand it. All right. So this is the merge method. Let's look at the sort method. Okay, remember merge sort is going to have only two methods. So this merge method and the sort method. Let's have a look at the sort method. So this method is taking 4 parameters. So we have the original array A, we have the copied array auxiliary, we have integer low, and we have integer high. Okay. Now we're going to determine the middle. So first we check if high is less than or equal to low, this means something is wrong, we should stop. That's like the base case. We find the middle, so integer middle equals low plus high divided by 2. And now we're going to sort the left side and the right side. Okay, we're going to sort the left side and right side. So left side is going to be from low to middle, and right side is going to be middle plus 1 until high. Okay, so we have the left side and we have the right side. Okay, notice that this particular method, the one I'm talking about, is private static method. There's an overloaded method which is called public static. Okay, so when somebody calls the sort method in this class, they're going to call the public method. And the public method, it takes only one parameter, which is an original array. Okay, so you can see this thing, what's happening in the sort method, the overloaded public one. So we create a new array of the same size as the original array. And then from here, we're calling the private method, which is an internal method. So we're passing in 4 parameters: the original array, the copied array, low position would be 0, high position would be the size of the array. So that's the entire code for merge sort. Okay, and here's the implementation for that. But sometimes my students do not follow this. So what I do is I do an example in front of you, so you will understand how things work out. Things will be a bit more clear. So let's look at an example.
It's two,
Sorry?
it's 2 recursive methods within each other.
No. We have, altogether, we have 4 methods. Okay, so there's a merge method and there's a sort method. So we have the overloaded sort method. Okay, and in the merge method, we also have, we had 2. One method for, for copying, one loop for copying everything to the original, and then the other loop. Right, let's have a look at this example. Things would be a bit more clear. So I'm going to put 8 values here, 8 random values between 1 and 10. Okay, so I'm going with 8 values just for the sake of understanding. All right. Now what we do is, again, 2-step process. We're going to divide it in half, and then we're going to merge it. So divide this in half. We're going to have, this is the half. Okay, so this is the left side, and this is the right side. Okay. Now what we're going to do is we're going to recursively keep dividing it until the size becomes 1. So let's go with the left side. If you look at the code, we call the left side first, and then we call the right side. So let's call the left side. So it's going to become 2, 8, 4, and 1. Then we're going to divide this again in half. So we have left side, and we have right side. Okay? Now we keep doing this again until the size becomes 1. All right, again, left side. So we're going to have 2, and we have 8. Here's the middle. Okay, so we're going to have 2 and 8. Now you notice that, okay, we have only one element. So we can stop the recursion here. This was our base case. Stops the recursion. Now we're going to call the right side. This also has only one element. So now what we do is we're going to call the merge method. Remember, the merge method creates an array of the original. So the size here would be 2. Okay. Now what we do is we take this value and we compare it with this one. This is smaller than this one, so we copy this over here. Okay, this was the left side. So we've exhausted the left side because the size was only 1. Now we're going to go take the right value and put 8 over here. Okay, so there you go. This part is done. Now, we go and look at the right side. Okay, this is 4 and 1. So we start splitting it. So we're going to have 4 and we have 1. So now we have size 1, size 1. Okay, we cannot split anymore. So now what we can do is we can create a size 2 element array. And now we're going to compare 4 compared with 1, which is smaller. 1 smaller, so 1 goes over here. Okay, and you go and check the next one. This is finished. There's nothing else over here. So we're going to take 4 and put 4 over here. So far, so good? So
Doctor, this is still the merge sort.
this is merge sort. So far, we're only talking about merge sort, simple merge sort. This is usually called top-down approach. Okay, so now we have the left side, which is this one, and we have the right side, which is this one. So let's try to merge them again. So now we're going to create a space 4. Okay, so now we're going to compare 1 with 2. 1 is smaller, 1 goes here. Next, we're going to compare 4 with 2. 2 is smaller, 2 goes here. Next, we compare 4 with 8. 4 is smaller, 4 goes here. Okay, now we've exhausted. There's nothing else after it. So we go take 8 and we put 8 over here. You see, now the left side is sorted. Now, we repeat the same thing for the right side now. Okay, so same thing is going to happen. But of course, this is going to execute after this is done. But I don't have enough space, otherwise I would go below this. But now, let's use this. So same thing happens here. We're going to split first. So we have 7 and 5. We divide this in 2 parts. So we have 3 and 9. Again, we go with the left side. So we're going to get 7 and 5. Okay, we cannot split anymore because now the size is only 1. So we can start merge. So here, 5. Yeah.
What we did in the slide before this, was it like different type, or what is, like, why is it 2 different things?
No, the same thing, exact same thing is happening.
But like, we're not comparing it to the original one, right?
We are. Okay, let me show you.
Okay.
So here we have 7 and 5. Remember the animation I showed you?
Yes.
So this is my original array. Now this is empty. Okay, here's I, here's J, here's K. Okay, compare 5 with 7. 5 is smaller, so we copy 5 over here. K plus plus, K comes over here. Okay, J plus plus, J goes outside. There's nothing else over here, so we're done. So now we go take 7 and put it at position K. 7 goes here. It's the exact same thing happening. Okay, so we're done with the left side. Now let's do the right side. So again, we're going to split this in half. So we have 3 and we have 9. Okay, again, merge these together. So this is going to give us, again, this is I, this is J, this is K. So 3 is smaller than 9. 3 comes here. I plus plus, K plus plus, K goes over here. Now we copy 9, put 9 over here. So we have 3 and 9. Okay, next step is merge these together, all 4 of them. Okay, so we have 5, 7, 3, and 9. If again, I would be here, and this would be J, and this is K now. So 3 compares with 5. 3 is smaller than 5. 3 goes here. Okay, J plus plus. This becomes J now. 9 compares with 5. The 5 is smaller, so 5 goes here. Okay, I plus plus. I goes here. Compare 9 with 7. 7 is smaller, so 7 goes here. I plus plus. We exceeded the limit of the array. So here we go with J. I can simply go and copy this over here. So we're done with the left side, we're done with the right side. Now again, I don't have enough room here, so okay, I'll try to put everything together. All right, now we repeat again. Compare 1 with 3. 1 is smaller. Compare 2 with 3. 2 is smaller. Compare 4 with 3. 3 is smaller. Compare 4 with 5. 4 is smaller. Compare 8 with 5. 5 is smaller. Compare 8 with 7. 7 is smaller. Compare 8 with 9. 8 is smaller. Okay, we've exceeded the limit, so we go and copy 9 over here. There you go. You have your sorted array. Okay, so in the exam, if I ask you to show me how you're going to sort, you have to show me this trace. Okay, we call this trace. This is how the algorithm is traced to show you how the sorting is working here. So from here up to here is the divide part. Okay, from here to here is the merge part. So again, it's always 2 steps: divide and merge. Okay. This algorithm is also called divide and conquer. Okay, divide and conquer. Okay, it's a very famous paradigm, invented perhaps by the British. So yeah, you divide your original data space and keep splitting it until it becomes really small, and then you start to merge things together to have the original data. Okay, any questions about this? If this is not clear, I can give you another example so you can follow up. Let me know.
Yes, doctor. I have a question.
Yeah.
How would this work for odd number of values, odds like 9?
Very good point. How is this going to work for odd number of values? If you remember the rule, we always split in the middle.
Yes.
But if it is odd, it's not going to be exact middle. It's going to be one element on the right side, one element on the left side. But if you remember the formula, how do you find the middle?
Low plus high divided by 2.
Low plus high divided by 2. Right. If the low is 0 and high is 9, okay, it's going to give you 9 over 2, which should be 4.5. But remember, this is integer division, so your middle would be 4. Right, now if you have an array like this, okay, so your left side is going to be a little bit smaller than the right side. 4. And then you have 5, 6, 7, 8, and 9. So your middle is going to be here. This is your middle. This is middle, and this is middle plus 1. So left side is slightly bigger than the right side. This is low, and this is high.
The one on the right, if we keep dividing, we will be left with just comparing one slot.
Again?
The one on the right, if we keep dividing, we will be left with one slot.
Always. Left to right, yes. So if you keep dividing, maybe on one side you're going to have 2 elements, on the other side you have only 1 element.
Yes.
It's okay. So now what you have to do is you have to divide the left side as the algorithm goes, and then start merging it. Okay? So let me do that particular example, what you're suggesting. Let's go with the smaller array of size 7. So let's say this is my data. Okay, that's my original data. we like to find the middle. So the middle would be, now the size is 0, 1, 2, 3, 4, 5, 6. 6 divided by 2 is 3. 0, 1, 2, 3. So it goes like this. This is your left side and this is your right side. Okay. So now next step is 3, 7, 5, 9. We split this in the middle. This is even, so this is like this. Okay, and we're going to have 3 and 7. So now we can merge these two. So we'll come 3 and 7. Okay, now we go and do this one. 5 and 9, split this in the middle. Okay, merge it. So we're going to have 5 and 9. Okay, now we're going to merge these two. So we're going to get 3, 5, 7, and 9. Now we go in with the right side. Okay, so here again, I don't have space, so I'll go from here. So we're going to split this in the middle. Okay, where's the middle now? So we're going to you're going to look at the position for this. Okay, so 0, 1, 2, 3. This is position 4, 5, and position 6. So low plus high, 6 plus 4 is 10, divided by 2 is 5, so it will be here. Okay, so my left side would be 2, 1, the right side would be 6 only. Okay, now again continue, 2, 1, split this in the middle, so we're going to have 2, and we're going to have 1. Now we start merging, so we're going to get 1, sorry, should be 1 and 2. Once you're done, we go to the right side. We cannot split this anymore because it's already only one element. So now we have to merge these together. So we're going to get 1, 2, and 6. Now finally, you merge these two together. So you're going to get 1, 2, 3, 5, 6, 7, and 9. So that's how you're going to go with the the odd numbered array.
Doctor, why is the middle not after 5? Between 5 and 9.
So go in the formula, Yani. The formula we're using is middle equals low plus high divided by 2. So here low was position 0, high was position 6. Divided by 2 is 3. So position 0, position 1, position 2, that's the middle.
Yes, right.
Okay, and this is middle plus 1.
Right.
So according to the code and the formula that we've seen, yeah, this is how it's going to go.
Okay.
Okay, so if this is clear, let's move on. Do you have any questions about this process? Do you understand it? Okay then.
The left side, we take the larger. For example, this 3759. Always we take the largest number on the left side.
What do you mean largest number? No, we don't looking at the values until we start merging them.
Okay.
So we keep splitting in half until the size becomes 1, and then you start comparing the values. But before that, no, we don't look at the values. Regardless of the value, you just keep splitting in half and half and half until the size becomes 1.
Okay.
Yeah, the comparison is happening only in the merge part. So we're merging this one with this one. Now we compare 3 with 5. The smaller goes first. Then 7 with 5. 5 is smaller. 5 goes first. 7 with 9. 7 is smaller. 7 goes next, and then 9 goes next. Here, when you're merging these two together, the 1 is smaller, so 1 goes, and then 2 goes, then 3 goes, 5 goes, 6, 7, and 9. Okay, so this is clear. Now let's look at why the runtime here is n log of n. Where the log of n is coming in from. Okay. So let's try.
Because we're dividing the array. We keep dividing.
Very good. We keep dividing the array. What's exactly happening is you have an array, and we're trying to split this in almost an exact half. Okay? Almost an exact half. It is possible that either left side is 1 bigger or right side is 1 bigger. But does it really make a difference if the size of the array is 1 billion? Does it matter that left side is one bigger than the other one?
No, it doesn't.
No, it won't.
No, it won't. Okay, good. So now what happens is, in the next step, we're going to split this in further half. Okay, and this will become half and half. And then again, half and half and half. So what's happening is here in the original data, the size was, let's say, I don't know, 16. Half becomes 8, half becomes 4, and half becomes 2, half becomes 1. So you can see this thing. We can give it by log of n. Okay? This is log of n. So this is where the dividing is coming up. Divide is taking log of n time. Now, the merge part, okay, merge part has to go with everything on the left side, everything on the right side, then we merge it together. So something from here goes here, something from here goes here, then goes here, then goes here, and so on. Okay, so this is O of n time. And every iteration is going to be a portion of O of n time. So what we do is we multiply all the divides with all the merges, and we're going to get n times log of n time. Does it make sense?
Yes, it does.
Okay, let me show you the slides now. Let's have a look at the slides now. Okay, so this is just a trace of that. Have a look at it carefully, how this is going from left to right. Okay, but after we've looked at our example, I think this should be clear now. Okay, here's animation. Some data, random data. Let's see what happens when we do merge sort on it. So notice we're dividing and merging, dividing, merging. See? So we did the left side. Now we're working on the right side. Okay? And now we're merging the whole two parts together. See? Did it feel like it was a bit faster?
Yes, doctor. It's clearly take each part, small parts, then sort each part, then merge them together after sorting.
Yeah, so we're dividing and merging, dividing and merging. So 2, then 4, then 8, then 16, and so on. So you will notice this thing. It will become a bit faster. But what if the data looks like this? Is it going to work faster? Same? More comparisons? More swaps? Yeah, remember we had this issue with insertion sort and selection sort. If the data is sorted in the other way for insertion sort, the algorithm becomes really slow. The runtime will be O of n squared. But if the data is in the same order, the runtime for insertion sort would be O of n, which is much faster. Let's see what happens with merge sort. Would it be any different? Here's the left side. And now we're making the right side. And here's the total. So, did it matter if the data was already sorted or random?
I didn't notice any big difference. There is a difference. There will be small difference.
Anybody else? Did you see any difference there? Nobody? Come on, there's only 1% in the class today.
It could be slower, but
No, there would be no difference, okay? Because we don't care about the positioning of the data. Our job is just to divide it, divide until it becomes only 1, and then we start merging it. So the runtime for merge, regardless of the positioning, is still going to be O of n. Cannot be any faster than that. Okay, so here's a very simple empirical analysis comparing insertion sort, whose runtime is O of n squared, with merge sort, whose runtime is O of n log of n. Like for small data, you're not going to see a big difference because they will work really fast. But for very large data, okay, if you try to sort 1 billion elements on your home computer using insertion sort, it's going to take 317 years. I don't know if you're going to wait so long. Okay, so for merge sort, it will take only 18 minutes. If you do the same on a supercomputer, okay, insertion sort will take a week, and merge sort will just do it very instantaneously, really fast. So what does that tell you? Which algorithm is faster?
Merge sort is way faster.
Super.
Merge sort is much faster. Right, here's a question. If you have a lot of money, okay, should we go and buy a supercomputer to make searching faster? Or should we invest in making a faster algorithm?
Faster algorithm.
It depends, Doctor, on my application. If I usually or do many complex calculation on a regular basis, a supercomputer would be, even though it's very expensive, it will be maybe helpful.
Because doctor, in the insertion sort in the supercomputer, for a billion it takes 1 week, but in the merge sort it's 18 minutes for the regular computer, the home computer.
Okay, here's a question for you guys. Do we have a supercomputer in Saudi Arabia?
I guess so, yes.
Yeah, we
Yes,
have in
Where?
Riyadh, we have in King Abdulaziz city. I think it's called Shaheen, and we have in Kaust.
No, Shaheen is in Kaust.
Shaheen is in Kaust. Then
We have two. There's Shaheen 1, Shaheen 2.
okay, then I'm sure that we have here something in King Abdulaziz city for technology and science.
Yes, there's one in Kaxt also. Okay, but how much money did it cost? Can a company buy a supercomputer, or does it have to be a government?
I don't know about the relation, but I think it's in the bulk part of millions.
Okay, see, the thing is, if you want to go with traditional supercomputers, they're very expensive. We're talking about tens or hundreds of millions of dollars, okay, for one computer. They're very, very fast, but they're also very expensive. But the other approach is using cloud computing, building clusters or renting out clusters. That's also possible. That's much, much cheaper, but then you don't have to own the infrastructure. So I usually teach this course, which is about cloud computing, how you can build your own supercomputer. Okay, it's very interesting. We'll see this thing next semester, how it goes. So bottom line here is, what we're trying to say is, yeah, if I want to spend millions and millions of dollars just to sort data, okay, I don't think it's worth it to buy a supercomputer. I would rather invest a little bit in finding a faster algorithm, okay, and use this on my PC or home computer. It's going to work faster. So good algorithms are better than supercomputers. All right. So here's runtime analysis. I'm going to show you a few slides with a little bit of maths there. Don't worry about it. I'm not going to ask you anything about this in the exams. Okay. So this is runtime analysis. How did we do this? Just a little bit of mathematics here. Runtimes for recurrences. Okay, this is proofs. How this works. So we're going to give it an equation. Okay. I skipped a lot of slides because I usually don't show it to the students not to scare them. But if you're interested, I can show this. I can share it with you. You want to have a look at it, or should I just skip it?
It's okay, doctor. We can look at it.
Okay, it's just a few slides.
If it's confusing, we can't skip it.
You cannot see?
No, if it's confusing, we can't skip it.
Okay. All right, this is a little bit of mathematics. So we can give those recurrences, okay, as a mathematical series, which can be given as log of n. Okay, here's evaluating this proposition that this satisfies this condition. Okay, so just a little bit of algebra, we can get something like this. Okay. Yeah, that's pretty much it. Again, some people get confused with this much amount of information. Anyways, now, so let's talk about a little bit of practical improvements on merge sort. Like, one important improvement is mixing merge sort with insertion sort. Remember, I told you a few minutes ago, we saw this thing, the merge sort's runtime is n log of n. Like, we didn't talk about the best case, worst case, average case scenario for merge sort. Can somebody tell me what's the best case for merge sort? Take a guess.
Big O of n log n.
Very good. Big O of n log of n. That's the best case. Wait, what's the worst case?
The same.
Same. Big O of n log of n. Get it? So for merge sort, best case, average case, worst case is the same. Big O of n log of n. Right. There's something really bad that we saw in merge sort, which was not there in the previous 3 algorithms we studied.
Oh, the space consumption?
Good. Space consumption. Merge sort is taking extra memory. The previous 3 algorithms we studied, they were not taking extra memory. So the algorithm that works in its own memory is called in-place algorithm. Merge sort is not in place. It requires more memory. Okay, so remember this. So it's working faster, but it needs more memory. Okay, there's kind of a trade-off. Now, the previous 3 algorithms, we saw that the best case scenario for insertion sort was giving me O of n time, linear time. So if my data is already sorted, if I know that my data is already sorted, I should not use merge sort. I should use insertion sort, because insertion sort is going to take O of n time. Okay? So here's practical improvements on merge sort. There's a proposition that when we're splitting the array in half and half and half and half and half, when the size becomes really small, let's say the size instead of 1, we stop at 8 or 7. Let's say the size of the subarray becomes 7. So when it becomes so small, instead of using merge sort, let's use insertion sort. Okay, why? Because when you keep splitting in half and half and half, remember we're using recursion. And recursion means that we have to use a stack built in the operating system, which is slowing down your computer. Okay, you're using the stack of the operating system. You're slowing down the computer system. So one proposition is we keep splitting, but we don't split it all the way until the size becomes 1. Rather, we stop when the size becomes 7 or 8 or 9 or 10 or something of this sort. So when it becomes really small like this, okay, instead of using merge sort, we'll use insertion sort at the end. So results.
So we have a formula, doctor.
Sorry?
Do we have a formula for like the position that we start insert?
Yeah, so I'm showing you the code here. So you see the white part in the gray box. We put this extra condition in there, that if high is less than or equal to low plus cutoff minus 1. So cutoff would be a number provided by you. We can say cutoff is 7 or 8 or 9 or 10 or something of this sort. Okay, we're going to apply insertion sort from there. Okay, so now what happens is...
I didn't get the formula. Can you just like please explain?
Yeah, so remember when we keep splitting this in half until the size becomes 1.
Yes.
Okay, that was a base case. But here we're saying don't continue until the size becomes 1. Rather, stop, okay, when you reach the cutoff point, when the size becomes the cutoff, whatever you defined. That's it.
So how do we define the cutoff?
It's going to be a variable, just a variable. You pass it, okay, as a global variable, you can pass it, and it will stop. And every time you reach the cutoff, it will stop there.
Okay.
So if I visualize it, you can look at it this way. So here's my total array. First, we go with the left, then we go with the right. We do the first merge. Okay. Now notice the size, we stop at 10. This particular example, let's say the cutoff was 10. Okay, so we do not make it smaller than 10. We stop at 10. It's very simplistic. And then we continue with the same sort and merge, sort and merge. Okay, so let me show you. This is another improvement on merge sort by eliminating the copy of the auxiliary array. Okay. All right. Now, what you need to know is in Java, when you say is arrays.sort, I'm pretty sure you've used this in CS101 and 102. When you say arrays.sort A, okay, Java is using the merge sort algorithm with built-in insertion sort. The cutoff is 7. Okay, cutoff is 7. So when you say arrays.sort in Java, in your Java program, okay, it by default goes with merge sort and a cutoff of insertion sort at 7. Okay, so we're done.
So always 7 as a constant.
It's fixed. Yes, it's fixed at 7.
So wouldn't it be better, and depending on the array, you would have different cutoff?
It would. I'm not sure if you can modify the cutoff, although you can implement your own version and make it even faster. Yeah, but again, based on empirical evaluation, they realize that 7 is a good number. Okay. Again, it depends on the performance of the underlying computer, the hardware itself. Remember, we said this before, when you do empirical evaluation, much depends on the underlying hardware and the software design of the algorithms. So yeah, based on many studies, 7 seems like a very good number, but this is where you should stop. Okay, so this is the first approach that we studied now. This is top-down approach. Okay, let me go back to the first slide. So this is the top-down approach. Let's have a look at the bottom-up approach. Okay, let's look at the bottom-up approach. So if you understood the top-down, understanding bottom-up is faster. Okay, so we have the same basic plan. We're going to have the divide and merge. Okay, sort or merge. Now the difference is, instead of finding the middle and dividing it by 2, and then finding middle and dividing by 2, remember every time you have to run the computation of the middle formula, which could be an added cost. So here what we do is we go with size 2, and then in every iteration, okay, we don't have to divide, we simply go and merge the data. Okay, merge 2, 2, 2, 2, 2, 2, 2. Then merge 4, 4, 4, 4. Then merge 8, 8, 8. And then merge 16, 16, 16 until you have the total data. Okay, so let me show you how this works. Let's have a look at an example here. So this is called bottom-up approach. So here's some data. Let's put some data here. It's random values. Okay, so here's some original data. Now, instead of finding the middle, we don't do that. We go with these 2 and merge them. So merging will make it 2 and 8. Then we go with the next 2. So this will become 3 and 7. Then we go with the next 2. So this will become 5 and 9. Then we go with the next 2. So this will be 4 and 6. Okay, so that's my first iteration. First iteration. Next iteration, here the size was 2. Next iteration, size would be 4. So we go with these 2. Okay, remember this is merge operation only. So we're not dividing, only merging. So we're going to get 2, then we have 3, then we have 7, then we have 8. Okay, now we go with these 2. So we're going to have 4, 5, 6, and 9. Okay, and now we do the same with size 8. So merge these 2. Now we're going to have 2, 3, 4, 5, 6, 7, 8, 9. Okay, does that look interesting? Or is it too confusing?
It's different approach.
The basic idea is similar. Okay, here we're not dividing. We don't have to find the middle. Rather, what we do is we go with size 2, 2, 2, 2, 2. Keep doing this thing until you reach the end. Then we go again. Start from the beginning. Okay, go 4, 4, 4, 4, 4. Then 8, 8, 8, 8, 8. 16, 16, and so on. So the idea is similar. Okay, but here we're not dividing. We are already going by the size. Okay, so implicitly division is still there, but we're going it upside down. So here we're going size 2, 2, 2, 2, then 4, 4, and then 8, 8, and so on. So again, the factor log is still there. Log of n is still there. But now, for every time we're going to do merge, so the merge will still take the same time. Merge would still be big O of n. So altogether, still n log of n. So there's no improvement here. It's still the same runtime. Let's look at how do we implement this approach. Okay, implement this would be much easier. Okay, this is size with 16. Okay, there you go. Here's the code for this. So notice here we have a sorting method. So merge would be exactly the same. There's no difference. But now sorting, notice one thing. We're using 2 loops. The first loop is going from 1 to n. The second loop is connected to the first loop. Okay, so theoretically speaking, this is kind of giving me O of n squared time. Okay, to be exact, O of n squared over 2, or series. But notice the jumps in the size. Size equals size plus size. Okay, so this is where the division is happening. Basically, it's not division, it's multiplication. It's going the other way around. So 2 becomes 4, 4 becomes 8, 8 becomes 16, and so on. So it's upside down, and still, okay, because there's a division or multiplication of 2, the runtime is going to be log of n. Okay, this is comparing top down with bottom up. Left side is top down, right side is bottom up. So I would say bottom up looks very neat. Okay, it's easier to understand the bottom up approach compared to the top down approach. But runtime for both of them would be exactly the same. Any questions about this? Is this clear?
Yes, Doctor.
Okay. Now let me show you one more thing, which is another sorting algorithm. It's called Quicksort. Okay. This gentleman, Tim Peters, he had an idea that the runtime for Mergesort, the best case, worst case, average case scenario is always big O of n log of n. So what he did was he put an extra loop before you actually go and check or apply the Mergesort. The loop is simply going to check if the data is sorted or not. Okay? So to check, just to check, we need to run one loop from 0 to n, linear loop. All we have to do is we have to see if the first element is smaller than the second element. The second element is smaller than the third element. The third element is smaller than the fourth element, and so on until the end. So if the loop goes all the way until the end without stopping, okay, this means the data is already sorted. We don't have to sort it anymore. Does it make sense to you?
Yes, it does.
Yeah. So the runtime, just to check if the data is already sorted or not, is big O of n. So this is what he did. Okay, this is what Tim Peters did. He added this one loop before the merge sort, and he called it Quicksort. Is this a good idea? Or is it considered theft?
Can you repeat what you just said?
I think it's
Asad?
a theft, Doctor. He just it's basically same idea, but with the small changes. Then he put his name on it.
Yeah. So very quickly, what he did was he invented Timsort. What he's doing is he took the whole code of Mergesort, but before running the Mergesort, he put an extra condition and a loop on top of it, checking if the data is already sorted or not. The runtime for this loop would be big O of n. So what he's suggesting is, if the data is already sorted, I don't have to go and do Mergesort. The runtime for Timsort would be big O of n. Okay, but if it is not sorted, the runtime would be big O of n plus the runtime for Mergesort, which is n log of n. So of course, when we're looking at the big O, we look at the bigger number. So we go with n log of n. Does it make sense?
Yeah, Doctor. In case if that it's already sorted,
Yeah.
Then it will be helping because the runtime will be less big of n instead of big of O of n of log n. But if it is not sorted, then we add another runtime to it as big of n plus the big of n log of n.
Yes, exactly. So the best case scenario is if the data is already sorted, we're going to spend O of n time to check. Okay, but now if the data is already sorted, we don't have to go and do merge sort. So the runtime would be big O of n. The worst case scenario is we go and check. Okay, check. So we realize no, it's not sorted. So we have to go and apply merge sort. Now, what he's saying is now the overall, because we're looking at a bigger term, so the runtime would still be big O of log of n. Does it make sense?
Yes, Doctor. Yes.
So what we're trying to say over here is that Tim Peters was trying to be a bit more clever. Okay, all he did a very minor improvement to merge sort algorithm. So what he did was he just put a simple loop before the merge sort to check if the data is already sorted. If that is the case, so the runtime, the best case will become O of n, which is really good. Okay, the worst case would still be big O of n log of n, which is still the runtime for merge sort.
Doctor, how about if I remove the for loop and if condition and put the cursive method of it? Would that work?
To check if it is already sorted or not?
Yes.
Its runtime is going to be very similar, still big O of n.
I think I will do that and then call it Ziad sort.
Of course, you're welcome. Yes. Yeah, we always have this laugh every semester. You can have a little play here and there. If you can improve it, go ahead. Very good. So this is a clever optimization. All right. Do we have time? Okay, let me show you just a few concepts and then we'll call it a day today. We'll do the tutorial inshallah tomorrow. So coming back to where we started from, so far we've known what is in place. What's an in-place sorting algorithm? Simple answer is if it sorts in its own memory, that's called in place. If it needs more memory to sort, that would be not an in-place algorithm. Right, now let's talk about stability. What's a stable sorting algorithm? Some algorithms are stable, others are not. Here's an example. Let's first try to understand. Example for Olympics. I'm sure all of you guys watch Olympics. I think this year's Olympics were canceled. It will be next year. So countries win medals. They go with gold, silver, bronze. Okay. The way they list the medals, they give preference to gold over silver. Silver has preference over bronze. Okay. So if you look at the table in front of you, you can see this thing on the top is United States with 46 gold, 29 silver, 29 bronze. If you look at China, 38 golds, 28 silvers, 22 bronze. If you look at Great Britain, They have more gold than Russia, 29 golds compared to Russia's 24. But Russia has more silvers. So they have 25 compared to Britain's 17. Russia also has more bronze. They have 32 compared to 19. See what's going on? If you look at the total, Russia has more medals. They have 81 compared to 65. But Britain appears at the third place because they have more golds compared to Russia. If the golds are the same, for example, look at Germany and France. Golds are 11, but silvers are different. Okay, Germany has 19 silvers, France has 11 silvers. So Germany is ahead of France. Does it make sense to you now?
Yes.
Yes.
In other words, we're also sorting by column. We don't have one index, we have multiple indexes in the same table when we're trying to sort things. But which algorithm works well with this kind of sorting? So an algorithm that takes care of these requirements is called a stable algorithm. An algorithm that does not is a non-stable algorithm. Okay, this is sorting by the total number of metals. Okay, some examples of sorting. So here's your music library. Okay, you're sorting by the artist. Here now, we're sorting by the names of the songs. Okay. So we usually follow the natural order. We already studied this thing last week. Okay, we saw the same exact code. The natural order is we go with larger to smaller. So we compare the year, then we compare the month, then we compare the day. If everything is fine, we return 0. We talked about this before. Now, we can define an alternate order. Okay, alternate order. So we have to look at total order. Total order. Okay, so these are some known things. Natural order example, now is the time. Okay, if you want to compare this time with a time in the past or the future, we're going to compare their years, and then the months, and the days, and the hours, minutes, seconds, and so on. Okay, case insensitivity. Here's another example. Example, I want to compare capital A with smaller a. How does that work? We look at the ASCII code, whichever appears first. Okay, the capitals appear before the smaller ones, so capital A is going to be before smaller a. All right. Some other languages have different rules. For example, cafe, C-A-F-E, E with a little hyphen on it. Is somebody taking Spanish? You know what? How do you pronounce this E? Cafe. Yeah. So if you compare this E with the other regular E, there's going to be a difference. All right. Phone books. If you compare names of people in a phone book, or even if you compare the letters or the words in a dictionary, we go with the order. Okay. So A, B, C comes before D, E, F, and so on. So the order is defined. Okay. Now, in Java, when you're using arrays.sort, most of the time you use the natural order. Arrays.sort and just pass it the array. It will by default sort everything in the ascending order, unless you provide it with a flag as a parameter. So you can provide string.case _ insensitive _ order. Okay, this is going to take care of the whole data regardless of the case. Okay, we can sort by language parameters. So so we're saying collator.get instance new locale ES. ES is for Hispana or Spanish. Here, if you pass AR, it's going to go with Arabic characters. Okay, we also have the by default British phone book order, so you can use that. So there's many different orders already defined. You can Google it and see which one is more appropriate for your application. Okay, so here's an implementation. It's just an example how you can write your own comparator. Again, we saw this before. It's nothing new. We saw these things before. Okay, so this is by defining your own order. So defining by the name, defining by the section. Okay, so it goes and takes care of it. So if you look at the left side, left table, this is sorting by student name. So you can see it's going with Andrews, Battle, Chen, Fox, Furia. So Fox and Furia, both of them are starting with F. Okay, so if O goes before U, so Fox appears before Furia. If you look at the right side, now we're sorting by the section. Okay, so now you can see this thing ordered by section. So 1, 2, 3, 3, 3, 3, 4, 4. So notice one thing. Look at the last two lines now. So for section 4, we have student name Battle and then Gessi. So you see that when we sort, first it sorts by the section number, then it's sorting by the name of the student. Okay? So an algorithm which is going to do something like this is going to be a stable algorithm. Merge sort is a stable algorithm. Okay? It is a stable algorithm. What you see in front of you, this particular one, this particular example is not stable. Because now if you look at section 3, we have Chen, then Fox, then Andrews, then Kangat. Andrews starts with A, should appear on the top. So what you see in front of you is the result of a non-stable algorithm. Okay, here's another example. So we have 3 columns. Let's look at the 3 columns. On the left side is sorted by time. Sorted by time. So you look, the times column is all sorted. We don't care about the order of the city. The one in the middle is sorted by location. Sorted by locations. You can go with Chicago, then Houston, Phoenix, Seattle. And then we're looking at the times, relative times. So Chicago, you can see this thing. The name is sorted, the name of the city is sorted, but now the time is not sorted. Like, if we consider both of them as keys, okay, so first we go with the name of the city, then we'll like to sort by the order of the time. This is stable, the result of a stable algorithm. Okay. All right. So without going into much detail here, because we're running out of time, so very quickly you should just know insertion sort is a stable algorithm. It's a stable algorithm. Selection sort is not stable. Bubble sort is not stable. Okay. Merge sort is stable. So that's a cool thing about these algorithms. If your data needs to be sorted in multiple keys, okay, I have multiple columns to sort, then you can use insertion sort, you can use merge sort. If you have only one key to sort or one column to sort, you can choose any of these algorithms. All right, so this is my last slide, runtime analysis of all of these algorithms that we studied so far. We talked about selection, insertion. We did not study shell sort because its runtime is no faster than merge sort, so we skipped that. We talked about merge sort and tim sort. So far, the fastest algorithm is which one?
Merge sort.
You sure? Merge sort? Best time is n log of n. We have something else?
Tim sort. And the average or the best?
Best case.
Best case is Tim sort.
Yeah,
and
tim sort and insertion sort. Both of them, their running time is big O of n. Like we always look at the big O and we look at the worst case scenario. So if you're looking at the worst case scenario, then we get tim sort and merge sort. Both of them, their runtime would be n log of n. Like when we're comparing the worst case of merge sort and tim sort, I would go with merge sort because merge sort is the original algorithm.
Add the list lines of code if that is something to consider.
Of course, it is to be considered. Yes, it's important. So overall, from all the algorithms that we studied so far, okay, the one that you can safely use, and you know that nothing else could be slower than this one. Oh, sorry, faster than this one. We go with merge sort. And remember, merge sort is also a stable algorithm. Is it an in-place algorithm? What's in place? Come on, don't forget.
One, we need more space for it. Yes, we need more space for Mergesort.
Yeah, in place means it sorts within its own space. It does not require more space. The merge sort is not.
It's not. Yeah.
It needs more memory. Okay, so this means that we're looking for an algorithm which is in place, which is stable, whose runtime is n log of n. We haven't found anything yet, and we'll leave it till tomorrow. Inshallah, tomorrow we're going to study Quicksort. Okay, so that's it for today, and see you inshallah tomorrow.
Doctor,
Yeah.
we have a heap sort where we use the heaps.
Sorry, come again? Okay, so I showed you the slide yesterday. Just the same thing, merge sort and quick sort. Did somebody tell me yesterday what the icon camel was for?
No, Doctor, you told us it's a pair.
Oh, I told you. Okay, so that's a Perl language. All right, so there you go. This is the Quicksort algorithm. Okay, you can print it out on a T-shirt. It's very simple, nothing complicated. Right. Let's try to understand the basic plan. Quicksort is a 3-step process. The first step, we just do it only once, and the other 2 steps, we do them recursively until the entire array of the data set is sorted. So first step is an important step. It's called shuffle. Okay, we simply shuffle the data in the original array. This step is really important. Okay, why? Because Quicksort has a worst case situation. It is possible to get a worst case situation for Quicksort, whose runtime would be big O of n squared. So to avoid the worst case situation, we do shuffling. Shuffling takes O of n time. So this is something similar to playing a trick with the merge sort. Yesterday we talked about Tim sort. Okay, so this is something of the similar nature. So we'll talk about this thing towards the end of the class today. Why is shuffle important? Next step is partitioning. Like in merge sort, we were always splitting the array in half. Okay, in the top-down approach, we were dividing everything by 2. Here, we're going to do something similar, but it's not going to be exactly in the middle. All right, so this requires a little magical thing called pivoting. So we find a pivot, and we're going to divide the array in 2 parts, left of the pivot, right of the pivot. Okay, everything smaller goes left, everything larger goes right. And the third step is a sort step. We recursively call the same array over and over again until the entire data set is sorted. All right. So let's see how this is going to work. But before that, a little history. Okay, so this was invented in the 1960s, 1964, 1961. Paper was published in Communications of the ACM. The author of this paper, he implemented the Quicksort algorithm in Algol 60 programming language. Maybe you've never heard of this, but it was a very important language in its time, 1960s. Of course, it's obsolete now. Nobody programs in Algol 60 anymore. So what he did was he implemented Quicksort, and he did some experimental evaluation. Okay. Bob Sedgwick took on his work. He produced a paper called Analysis of Quicksort Programs, published in 1976. Okay, I believe this was his PhD thesis. So what he did was he refined the Quicksort algorithm, and because of his analysis, because of his work, Quicksort became very popular. Remember, Bob Sedgwick is the author of the book that we're studying. Okay, let's have a look at how things work. So I'm going to show you the partitioning method now, little animation. Let's try to focus on how this works, and then we're going to get back to a few examples, and we're going to see or apply that. Okay, so here's my original data. Here's my original data. We would like to sort it. So remember the 3 steps. The first step is shuffling the data. So shuffling is just like when you're playing cards, you shuffle the cards. You try to put them in random order so that to ensure that the cards are not sorted in any way to give any kind of unfair treatment to one of the players who's playing the game. So here we have the similar situation. We like to shuffle the entire data, making sure that the data is not pre-sorted. Okay. Remember, this is completely opposite to what we were trying to do with insertion sort. In insertion sort, we try to go and check if the data is pre-sorted, which means we don't have to go and do the expensive sorting. But here it's the opposite. Here we're saying we want to make sure the data is not sorted, okay, to apply Quicksort. So similar to what we did with Mergesort, we used to define a low, a high, and a middle. Here we define 2 pointers, I and J. These are pointers that are going to move. So I will go from left to right, J will go from right to left, and we define a pivot variable, okay, which is at the position low. Position low. So this is pivot. Now here we're assuming that the data is already sorted. Data is already, the data is already shuffled. Now what we do is we define the first element as the pivot. I is going to be the one after pivot. Now our job is to compare the values at positions I and J. Again, we're going to compare the values at positions I and J. Okay? If one is smaller than the other, we're going to exchange them. If not, we keep moving. So let's start. So right now, I is at position, I is pointing at R, J is pointing at S. Okay? We're going to compare R with S.
R is small up there, so stay.
Yeah. Sorry, we're going to compare R with the pivot value, K. Okay, R is larger than K, but S is also larger than K. So remember, we always keep the smaller values on the left side, smaller than the pivot. We always keep the larger values on the right, larger than the pivot. So now what happens is R was larger than K. So we stop at position I, we don't move it. Okay, now we go with the right side. So J was pointing at S. S is larger than K. That's okay. Remember, S is larger than K. It should stay on the right side. O is larger than K. It stays on the right side. X is larger than K. It stays on the right side. C is larger than K. No, stop. So we try to go from left to right using I. Okay, remember we want to keep the smaller values on the left side. R was larger than K, so we stopped there. We did not move I. And then we started working with the right side, which was J. And now we're checking all the elements which are larger than K, which is the pivot. So S was larger, O was larger, X was larger. Now we stopped at C because C is not larger. Now what we're going to do is we're going to swap, exchange R with C. Okay, we exchanged R with C. Now what happened is C is smaller than K, so it stays on the left side. R is larger than K, so it goes on the right side. Now, continue. We have to keep doing this thing until I and J cross. All right, let's see. I is going to move. A is smaller than K. Yes, we move I again. T is smaller than K. No, we'll stop here. Now we're going to move J. So Q is larger than K. Yes. M is larger than K. Yes. I is larger than K. No, I comes before K. So we stop here. And now we're going to exchange T with I. Okay? So this was the second swap. Continue. Let's go. E is smaller than K. L is smaller than K. No. So we stop there. Okay. U is larger than K. Yes. P is larger than K. Yes. E is larger than K. Yes. No. Okay. So what we do is we swap them. Okay. So again, repeat the whole thing again. So I move on. Okay. Now remember here, I and J are crossing now. Okay. I and J are crossing. But right now, what's happening is L comes after K. So we don't have to move I. Now we check with the right side. L is larger than K. Yes. So we move towards the left. The moment you exchange, the moment you cross I and J, this means we have to stop here. Now what we do is we're going to swap. We're going to swap the pivot with the J value. Okay, we swap the pivot with the J value. So this was the original position of K. This is where K is supposed to be after sorting. Now notice everything on the left side of K is smaller. Everything on the right side of K is larger than K. So this is the correct position for K. All right, so this is simulation. Now I'm going to show you a few examples on how this is going to work. Let's have a look at an example on the board.
Doctor, I'm sorry, but I didn't understand why you changed the K with I or J.
Okay, let me go over this again. I know this could be a bit difficult for students to understand, but let's look at another example. Things would be a bit more clear. So I'm going to create an array of, let's go with 8 to 9 values. All right, so okay, so let's say this is some array. I would like to sort it in ascending order. So let's also assume that this is already shuffled. Okay, let's assume this is already shuffled. So what we do is we're going to pick a pivot, usually the first one on the left side. This is my pivot. I'm going to define I and J. Okay, I goes from left to right, J goes from right to left. Right. Now what we do is we're going to compare each value with the pivot. If it is smaller, I moves right. Okay, so we go 2 is smaller than 8. Yes, so we move I over here. 3 is smaller than 8. Yes, so we move I over here. 6 is smaller than 8. Yes, so we move I. 5 smaller than 8. Yes, move I. 4 is smaller than 8. Yes, move I. Okay. 9 smaller than 8. No, stop. Okay, so we stop here. Now we go with the right side. So we go this way. So 1 larger than 8. No. Okay, it's not. So we stop here. Now what we're going to do is we're going to exchange the positions, the values at position I and J. So this becomes 1 and this becomes 9. Okay. Now continue. This becomes I. Okay. And 9 is smaller than 8. No, stop. J moves over here. Okay. Notice the moment J crossed I, this means stop. We're done. Now what I have to do is I'm going to swap this value at position J with the pivot. Okay, so I'm just rewriting it. So 1 comes here, 2, 3, 6, 5, 4. This was 8 now. This was my original pivot, and this is 9 now. Okay, so far so good.
Doctor, can you repeat the last step?
Okay. Yeah, last step was when I and J cross, okay, we stop. the value at position J would be swapped with the pivot. So we swap 1 with 8. So 1 comes here, 8 goes there. This was the last thing we did. Okay? So
we always start with I or J.
Sorry?
We always start pivoting with I or J.
We start pivoting? What do you mean? The pivot is
No,
always
not pivoting. We start traversing with I, moving I or J first.
First I goes from left to right. J goes from right to left.
Okay.
Okay. Is clear? Not clear? I can pick another example if you like. Not clear?
Yes, one more example to make sure.
Yeah, it's clear. I think the clarity because the pivot always appear on the most left. Then we say this will be to its left and others will be to its right. But it's clear now.
Okay. Let me do this thing again with a different example. Okay, so assuming that this is already shuffled, we're going to pick 1 as a pivot. The first value that becomes a pivot. This is I now, and this is J now. Okay, so again we compare. So 9 is smaller than 5. No, so we stop I over here. We don't move it. Okay, this means we're going to swap this one. Now check this. 3 is larger than 5. No, it's not. Remember, for I, okay, array of I must always be smaller than the pivot value, okay, A of low. And for the right side, A of J must always be larger than the pivot. So in this case, both of them are wrong, okay, which means we stop there and we're going to exchange them. So this becomes 3 and this becomes 9. Okay, so again, go again. So this will be I now. 1 is less than 5, yes. So we're going to move I. 8 is less than 5, no. So keep I over here. Move to J now. So previously we did this thing, J comes here. 7 is larger than pivot 5, yes. Okay, so move J. 6 is larger than pivot, yes. So move J. 4 is larger than pivot, yes, no, stop here. So we're going to exchange that. This becomes 4 and this becomes 8. Okay, again, we already did this thing for I, so I comes over here. Now we're going to see this. 8 is smaller than 5, no, so stop here. J comes over here. Okay, and since J has crossed I, so we stop. Now what we do is we're going to swap the J position value with the pivot. So this is my first iteration, first swapping, or first traversing. Now what's going to happen is we're going to swap 4 with 5. 4 comes here, 3, 1. This becomes 5. This is 8, 6, 7, 9. Okay, so did the whole thing again with a different example. Does it make sense now? Is it clear?
Yes, it's clear now.
Okay, good. So now we have 2 parts. This is where the partitioning or division is coming. So we have the left part, and we have the right part. Okay, now we're recursively going to do the same thing again for the left part and right part. Now assume that, okay, this is the new data set, and we'll have to repeat the same thing again. So we're going to define a pivot. Let's say this is my pivot. Okay, this is pivot. Here's I, here's J. So again, repeat the whole thing again. So 3 is smaller than 4, yes, move I comes here. 1 is smaller than 4, yes, move I. Okay, we crossed I, we cannot move anymore. Okay, and J is at 1. All right, so 1 is larger than 4, no, stop. J is already crossed I, so now what's going to happen is we're going to swap these. So we're going to get 1 here, 3, and this is my pivot 4. Okay, so notice for this particular data set, we have a left side down, but there's no right side. Okay, let's repeat the same thing over here. So this becomes the new pivot. Okay, here's the new pivot. Now we're going to define I and J. So again, repeat the same process. 6 is smaller than 8, yes, I goes here. 7 is smaller than 8, yes, I goes here. 9 is smaller than 8, no, stop there. Okay, I move J. So 9 is larger than 8, yes, J comes here. Notice we've crossed I. Okay, so you don't even have to go and check this. You don't care about that. All we have to do is we have to swap 7 with 8 now. So if I rewrite it, okay, so 7, 6, 8, and 9. There you go. So now this one has a left side, right side. But we continue doing this thing until the size becomes 1. Okay. So next step, next iteration. Let me do it with the blue color. So again, repeat the same process. We're going to have 1 as a pivot. Okay, here's I, here's J. Both of them are at the same position. So now we check. I, yani 3 is smaller than 1, no. Okay, go with the right side down. J, 3 is larger than 1, yes. So J goes over here. It has crossed. Now what we do is we're going to swap J with the pivot. It happens that J is also this, so we don't have to actually swap anything here. Okay, so we're going to write 1, and now we have 3 on the left, on the right side. Okay, so there's only one element over here, which means we don't have to sort it anymore. Right. Let's go and look at this one. Here we pick this one as a pivot. Again, this is I and J. Okay, so again, 6 is smaller than 7. Yes, I goes over here. It has crossed. Okay, now what we're going to do is we can simply swap 6 and 7. So we're going to get 6 over here. Here's 7. Okay, and this was all alone. There's nothing else with it. One element, so we don't have to sort it anymore. Right, we're done. Now, notice one thing. If I rewrite the contents of this, let's say, array, I have got this. I have 3 here. Sorry, I have 1 here, 3 here, 4 here. I have 5 here, 6, 7, 8, and 9. Is it sorted?
Yeah, yes, doctor, sorted.
Yes.
Okay, so this is how Quicksort works. Okay, it looks a bit complicated, but it works really fast. Okay, and this also happens to be an in-place algorithm. Remember in place from yesterday?
Yeah, it means that
It's no more space needed.
Yeah, no extra space needed. So it works in the original array, no need for extra space. Mergesort was not in place. It required extra memory. But this one does not require extra memory. So from the memory perspective, if I'm comparing Mergesort with Quicksort, Quicksort, of course, is a winner because it does not require any extra memory. But now let's talk about the time. How long is it going to work? Do you notice something that we're splitting the array in kind of halves every time? So we have a left side and we have a right side. And then again, we have a left side and a right side.
Log of n.
No right side. Again. So every step we're doing left, right, left, right, left, right, left, right. Yeah, kind of we're dividing everything by 2.
Is it log of n?
Which is giving us log of n. Okay, that's how you're getting the log of n. And we're doing I and j, okay, over and over and over and over again. How many times? Okay, maximum is n times. So you have to multiply n with log of n. So this is just an overview, just a high-level understanding. Let's go back to the slides. Let's see the runtime for this. Oh, this is from the Mergesort. Okay. All right. So here's our code. This is how things are going to work. This is the partition method. Partition method takes the original array, takes two parameters, integer low and integer high. Okay. So we're going to define I as low and j as high plus 1. I need the last element in the array. Now we have loops. The outer loop runs forever, infinite loop. It is going to be stopped by a break condition. Now inside this, now we're going to go from left to right and then from right to left. So the first nested loop is controlling I. Okay, so it goes from the leftmost position, okay, until we find a value which is larger than the pivot. So this is where this comparison is coming in. So we're comparing less a of plus plus I with a of pivot. Okay, so if the value at position I is larger than the pivot, we're going to break. Or we can also break if we reach the end. Okay, after this, the second loop, which is going from right to left. So again, we're comparing pivot with the last value in the array. Okay, we're moving leftwards. We're doing minus minus j. Right. Whenever they cross, yani I becomes larger than j, we're going to break, stop the outside loop. Okay. Otherwise, we simply go and exchange the positions or the values at position I and j. Okay. So this continues until we've crossed I and j. So the nested loop is going to end. And after this, we're going to exchange the pivot with the j value. And at the end, we're going to return the j value. This is partitioning. Okay, this is the rest of the code. So we have sort method. Okay, there's public and private one. So in the public method, notice the first step is shuffling. So this is defined in standard random library. Okay. You can create your own method for shuffling, and then we call the nested, the recursive sort method, passing in the original array. Left position is 0, or the lowest position is 0. Highest position is the last position in the array, which should be a.length minus 1. And now if you look at the private method sort, okay, you can see that we can stop this. The base case is when high becomes less than low. Okay? We're crossing, or the size becomes 1. Okay, size of the array becomes 1. So we don't need to sort this anymore. And then we find the j position as partition. Okay, notice the partition, we saw this thing before on the previous slide. And then we go left and right. So we have the recursive sort on the left side, the recursive sort on the right side. So that's the entire code for Quicksort. Now this is a trace, so we already saw a few examples for this. Okay, if you want, you can have a look at it again. Now here's an animation showing you the runtime for Quicksort. Let's see what happens. This is a random data. Okay, I remember there was an issue with this. So it's going to work fast, almost as fast as Mergesort. Okay. So some cool things about Quicksort, it's a in-place algorithm. It does not require extra memory. Okay. To stop the loops, we simply check if j crossed I, and j becomes smaller than I. Okay. If there's duplicates available, we can also stop the scan. Okay. It also preserves randomness because of shuffling. Okay. Now, the original paper, which was published in 1961, they did some experimental evaluation. They implemented the Quicksort algorithm using Algol 60 on a computer called National Allied 405 computer. Okay, it had a magnetic disk. You see a picture of the magnetic disk. Notice the size of this disk is 16K words. Remember, one word is equal to 2 bytes. So the entire hard drive size is 32 kilobytes. Nowadays, if you take a photo with your mobile phone, it's going to be a few megabytes just for one picture. Anyways, so they compared the runtime for Mergesort with Quicksort, and they noticed that Quicksort runs faster than Mergesort. Notice, theoretically speaking, the runtime for both of them is big O of n log of n. Okay, but in empirical evaluation, experimental work, we notice that Quicksort works faster than Mergesort. Okay, here's a comparison now. So we're comparing insertion sort with merge sort and Quicksort. Notice last time we compared insertion and merge sort, and we saw that merge sort was much faster than insertion sort. Now we're comparing Quicksort with merge sort. So you can see this, they're relatively comparable. Okay, Quicksort works a little bit faster than the merge sort. So we looked at this lesson yesterday, which was good algorithms are better than supercomputers. Today's lesson is great algorithms are better than good ones. Okay. So here's a little bit analysis. If somebody asks you, how can you prove that Quicksort runs in n log of n? Like for merge sort, it was easy because we were almost always dividing everything by half. Here, it's not always half. Okay, so now we have to be really careful. So assuming that this data is given to you, okay, we notice that every time, this is by the way the best case scenario for Quicksort, every time pivot appears exactly in the middle. Pivot appears exactly in the middle. Yani the left side, the length of left side is always equal to the length of the right side. So this is going to give you the best case scenario, the fastest possible time. And the number of comparisons here is going to be almost exactly n log of n. Here's a worst case scenario for Quicksort. What if the choice of pivot is not good? Okay, what if the pivot is always smaller than the rest of the array? So this is what is going to happen. See that? Now the runtime is going to be half of n squared. This is something which is worse than n log of n. So to avoid this, notice that the data is already sorted. The worst case appears only and only if the data is already sorted. So what we can do here is we can put just a simple loop in the beginning of the Quicksort, and this loop is going to ensure that the data is shuffled. If the data is shuffled, okay, you're never ever going to get the worst case scenario. So we saw the best case and worst case. Let's have a look at the average case. Remember, average case requires a little bit of mathematical work. So I'm just showing you a few equations here. Okay, don't get scared with this. So this is the estimated runtime for partitioning. Okay, so you can see a series over here. You can give it by a little bit of algebra. You can solve this equation like this. Okay, rearrange the terms. Distant valuation of the same, and you can give it by an integral. So this is the runtime, average case runtime for Quicksort. Okay, so it's going to be 1.39 n log of n, which is very similar to the average case runtime of Mergesort. Okay, so there are lots of performance improvements on this, but we're not going to go into much detail here. Okay, so what we want to know is the best case scenario for Quicksort is exactly n log of n. The worst case scenario is half of n squared. Okay, but if you put the shuffle, okay, if you put the shuffle before the Quicksort algorithm, the runtime would be n log of n. Right. What's the probability that even after shuffling, the data is still sorted? Is there a chance for that to happen?
No, doctor. Maybe a very small chance.
Theoretically
I
speaking,
don't think so.
there is a chance. Theoretically speaking, there is a chance. Okay, but they've put this little note here in the gray color. It's more likely that lightning bolt strikes this computer during execution. Okay, so there's a very little chance that could happen, but theoretically speaking, yes, it can happen.